在录制此会议。
Welcome back. So the beta analysis give you some information and how we have the corresponding formula label. The other thing is that those are the demonstrations. So what is the corresponding depletion region and the potential relates to the gen induced voltage. So the at equilibrium that the area potential is fixed and we no longer have any high frequency response. What happened here is that you can go back to the previous slide that we get the depletion region. We call it the phi surface potential equals to 2 phi s. So you get it without any drain voltage. That is that the depletions that we get the inversion layer, which is phi surface equals to 2 phi f. And then at non-equilibrium, that if you get additional reverse bias at drain. So the first one is you get a certain depletion region, and then the maximum depletion determined by what is the corresponding doping concentration QNA. And this one is WD, the depletion region, maximum depletion region, because we apply the drain voltage. The next is the additional external voltage. Remember, it's not fine. We call the equilibrium and the non-equilibrium. Do we have any external voltage we apply? Okay. For external voltage we applied, we will split away the maybe not away, accumulate or away the meiotic carrier. So it will change the state or carrier distribution of the drain to gate side. Okay. So we can see that when applying the higher reverse bias at the drain voltage, using the drain voltage, you get this depletion reaching further away. Just like in the previous Venn diagram, you can see that the depletion is intense. So you get a larger depletion region here. And for the one in which we pierce down, it is the accumulation mode. The depletion region, even it is maximum, but it will be still smaller than the one we are working with the drain voltage. And that will increase the maximum depletion region. So you can think that if you apply the drain voltage to drain the current from the drain side, you get this quasi-Fermi label. We split the Fermi label further, and you get this curve further down. And you get a surface potential which is much larger than the previous one. And you can think that in this case, the total phi x is equals to the phi f 2 phi plus additional voltage Vd. Okay, so you can think that by applying the additional voltage, we split the Fermi label, and the initial Fermi label is determined by the 2 phi f, or you can say the gate voltage. So you get these two effects summarize the data. So there will be an assumption that the majority carrier quasi-Fermi level phi EFP is still the same. Okay, so remember that we talked about the quasi-Fermi level as the majority carrier before. So if you get the majority carrier, that we get the N-type doping, type and the P-type, they are still staying in the same way, corresponding to the conduction and the valence band. So they are still at the same side. But if you look at the majority carrier in N-type and the P-type system, in P-type systems, the majority carrier electron will be least. Okay, so this will move away from the conduction plane. Remember that for quasi-Fermi level EFN, describing the Fermi level for electron, if it moves away from the conduction plane, that means the carrier concentration will be least, will be lower. So you can see this one is the mild carrier. And how about in N-type region? In N-type regions, this EFP, the multi-carrier of hole, will move up because it will move away from valence band. That means you get this carrier concentration of the whole area. So you split the Fermi label, but the split one will be only related to the multi-carrier by the drain voltage. Okay, so before we apply any drain voltage, the Fermi level will be still the same for both EFN and the EFP. There's only a simple Fermi level. But later on, when you apply the reverse bias and the drain part. It's just like a reverse biasing for PN junction. We split them terminable for minority carrier, but for the majority carrier, that will still remain the same. Okay, so before we talk more about the detail and the biasing code, I want to show some conditions similar to the BJT. So in BJT, we talk about some small signal model, especially if you have an AC analog signal and a high frequency response. And then the similar thing happens for the MOSFET here. So let me first talk about the large signal operation. So for large signal operation, typically you get the conducting current as we labeled here. So let me find the slide first. So typically, again, so we can say for this operation, so we still first biasing the MOSFET and then trigger a signal as the AC component. But for MOSFET, there will be additional difference in comparing with BJT. What we mentioned for BJT is that most of the circuit is used in analog circuit, so we want to amplify the voice, to amplify the analog signal. But for MOSFET, it can do both. You can amplify the signal, analog signal, or you can have digital circuit of application. That is the most adapted for MOSFET. But my question, my risk is that for BJT, we also talk about it is possible to do logic, right? It is an inverter. How we do the inverter for MOSFET, BJT? We just turn on the B side, VB. If your input in VB is high, that means you get a current flowing through, so the voltage and the output should be low, right? If your input at the B side is low, that means you turn off the voltage of B side and you turn off the current. So there's no current flow from collector and there is no voltage drop for RC. That means you remain output voltage as high voltage, right? So it can work as inverter. Similar thing can happen here if you connect the circuit like the MOSFET. You can operate the, maybe I join. You can operate the MOSFET. Typically, it is a MOS, and then here is the source side, here is the drain side, here is the gate side. So it is a really simplified model. You get a isolator here, so it is a gate function. When we apply gate voltage for NMOS state, so here's NMOS state. It is conducting with N channel, electron channel. So when you conducting the electron channel, the voltage should be positive. And once you have positive voltage, you get some negative charge as the channel, and then we get channel flow, current flow from drain to source. And for this combination, what you previously mentioned is that always we have the gate combination in which we forward biasing to have the accumulation of the silicon bound. And the latest once you connect with the area, we want to do reverse biasing to the PN side, right? So here is NPN. So for reverse biasing, we want to have positive voltage. Okay, so this connection is pretty similar to what we did for BJT. And the other is the constant. What we check here is that here is the input signal. Here is the output signal. Okay, so for output signal, typically you get additional RD, the drain resistance. We will talk about more detail about how do we operate the current, but you can consider, okay, once we have the drain current, what happens is if your input, here's the input, maybe I make it as a table. Here's the output. If your input output voltage here's out. Okay. So if your input voltage is high, like a label of 1 and label of 0. It is typically 5 volt. Here's typically 0 volt. If you play with 0 volt, what does this mean? You turn off the channel, there's no current flow. Once there's no current flow, what is the voltage of the output voltage? Maybe I draw here's the output. Sorry. Here's the output. If you connect the output here, there's no current, so there's no voltage drop along the resistance. So how much voltage we supply here equals to the voltage we measure. So under that's a constant, that will give you a high voltage at the output. But if you connect with the high voltage as the input, what happens here is you get a large current. You get a large current flow, you get a voltage drop along a D, and then you get a certain voltage along here, but just 0.2 or 0.3. So you can label the output to 0. Okay? Now we will try to draw the transfer curve, but you may consider that under this constant, it will work as an inverter. But one question is that, what is the difference between BJT and why we didn't just use BJT as our very large silicon integrated circuit? Why we only use MOSFET? So we can, since the years before we have the MOSFET invention, we can only apply the BJT. And the BJT it works, but it typically works in your headset and stereo, headphone, and also microphone. It increases the amplifier of analog signal. And why we didn't use it as the digital signal? What is the main difference between BJT and the MOSFET? I was also receiving these questions when I was a graduate student, the first year in a semester student. I'm actually surprised no one can answer it correctly. A lot of people mention because it's simple. Both are simple. You can see doping, NPN, PNP. Even for MOSFET, we need to add an extra layer of insulator. So what happened? What is the benefit? So actually, the benefit is simple. What is the power efficiency? You can think that how do we operate the BJT? We have the collector emitter. We have a lot of current transfer from emitter side to collector side. We drain the current from collector side. But if we have some leaky current to base, right? Even if the ratio is high, only 1%, we get the beta as 100, right? So we get a certain high base, the base current flowing at the base. So only maybe 1%. But that will be significant. For instance, if you conducting current at, I'm not sure, 1 mA or 100 microamp, what is the current? So for instance, lower current, 100 microamp get 1 microamp at the base current. You sum that's fine. Only 1 microamp, right? You get a leakage of 1 microamp. It doesn't really matter how do you operate it, right? Because once you turn it down, there will be leakage current. Okay? So 1 microamp, but we get how many transistors, right? Trillion transistors. How many leaky current? Trillion multiplied by 1 microamp. Get like 10 to 16, 10 to 6. That's a huge number, right? You just burn out your devices. How about you use the microwave? Yeah, so you can eat it with the chip, eat your food with chip. People can work easily in your lab. It's not going to happen because every energy supply just like the waste. Okay, but what happened for MOSFET? When you turn it down, turn it off with the gate voltage, is there any current from gate to outside? No, there's not. That means there's no leakage, there's no waste current. Okay, that's the power. So while we work with MOSFET, and we can build up MOSFET into a really trillion circuit. The reason is because when you operate the MOSFET, by turn up, turn E, turn on, as long as you do not have additional resistance or loading, you do not have any leakage. You do not have any power dissipation. So that's meaning that. But of course, we need that because there's still biasing component like the RD, as we mentioned. But if you just consider the operation, there's no leaking current to the gate side. So there, when you control it from the control part, there's no current and there is no heat accumulation for the entire circuit. That is the most important part. When we work with logic device, we want to build up with a million, trillion number of transistors. But for each transistor, unit should be efficient. Only 1% power you save, you get is expected to happen or it is possible. So please remember, we only change a really small concept. We change the driving current from induction current to drift current. We have certain gain outside here. We can build up different things. We can make things happen. So that is the most important part, especially comparing with the current we measured here. Okay. So any questions? Certainly it is the most essential part of the MOSFET. And the next I want to talk about the operation, especially logic circuit and in the in motor part. Okay, so if there's no additional question, let's begin this part. So it will be pretty similar to the microelectronics before, but as I mentioned, it will be also essential to know the logic signal model. How do we connect the simple and how do we apply this MOSFET to a digital circuit? Okay, so for most of the almost connections, we already give you an example. And maybe for this symbol, sometimes you will get a sound symbol like this. Okay, so it is still denoted the source. But why we have additional connection here when you play with PSpice, for instance? The reason is because it will be a substrate voltage. And typically the connector substrate the same voltage to source. That means they grounded the source together with the substrate. So you should have always the reference potential referred to the substrate. That will fix what we mentioned before. So we consider the most adapted connection. First, we have RD here connected to VDD. And here we have the input, the output voltage. Okay, so that's what happened here. So that's what we have the NMOS inverter. And why we call it inverter, we already showed here. Because when you have high input, we get low output. We get low input, we get high output. So how it works, like the binary condition. So you can say we want to work with the binary deal, which we get a low voltage. And the one, we get a high voltage. Okay. So what happened here is again, we try to draw the curve. ID. Here is the current flow along the resistance ID. And then here is the V output voltage. Or you can say VD, the drain voltage at the transistor. When you give this scheme, what happened here is you first draw the current. As we previously mentioned, the current will be something like this. Okay, so what does this mean? This means that previously we have a trial region, we have the saturation region. That's what we had. And why we have different tracks? The reason is because we get a different VGS. Okay, so for instance, VGS minus VT equals 1 volt, 2 volt, 3 volt. Okay, so we can think that here VGS minus VT, V equals to 0.5 volt, VGS minus VT equals to 1 volt, Okay, you get maybe a high VGS. And why we have this saturation current? Because the saturation current based on this previous derivative, we get 1/2 UN CR sine W/L VGS minus VT squared. Okay, so once you fix the VGS, minus VT, you get a constant trend. It should be independent to VT. Okay. So under these schemes, we can notice what is the corresponding relationship when we look at the different potentials. So we can start with like the load line. So what is the load line? So what is the relation of the RD? So load line will depend on what is the VDD minus ID minus RD multiplied with RD equals V out. Okay. So the voltage is supplied here minus the voltage drop along the RD equals to output voltage. So what is the relationship here? So we get ID, we get the I out as these two factors. So you can think that you consider, maybe you just draw point. It is a linear relationship. If you consider the VD equals to 0, what happened here is that you get output is 0. The ID equals to VDD over RD. Okay. And how about if you consider ID equals to 0, VDD equals to VL? So you get two boundary conditions. Okay. Once you get these two boundary conditions, it should be like a slope here. When you connect these MOSFET transistor with RD and then bias in the current like this, that is what happened. And the cross section region is the solution. So here's the solution. And then you can see what is the slope. Slope is equals to you can take this as a y. So you get this VDD as the output. So over RD. So it's 1 over RD. Right? So let us consider some point. First is the lower point, in which we call it A. So for this one, maybe I use different color. Consider this is an A point. What is A point? This one, because the output is we should sorry. We should start from point A. For point A, what happened here is that your VGS is smaller than VT. Okay, when VGS is smaller than VT, what do you get here? So you get no driving current. You get this V out as high voltage. Point A. So we label this one as point A. And then times we call the second point here as point B. At the B point, what happened here is that your VGS minus VT, which is you get a VGS minus VT is high, so you get the transistor conducting, so you get current. But once you get the current flow, what happens here is your VDS is also high at this moment. That means you get this VDS first as a high voltage. But later on, it will dropping. So you first get the VDS is high, so you work in saturation region. But later on, it will go back to the trial region. When you work with the trial region, that you need to use the equation VGS minus VT multiplied with VDS minus 1 over 2 VDS squared. That is what we described in the previous slide. So for this trial region, we can denote it as VGS minus VT is larger than VDS. So VDS is small, and this one is in trial region. Let me just recap. What we get is ID equals to mu n CR psi W over L VGS minus VT VDS minus VDS square over 2. Also, since this VDS is really small, maybe you can get rid of this part. So that's what will happen in linear region. So we previously say it is in linear region, right? In linear region, it should be proportional to VGS minus VT and the VDS. And what we get here is that, okay, so I want to calculate is the corresponding RDS. So you can think it just like a resistance in parallel. But why we can calculate that is because we get ID and the VDS, the V out. Okay, so if you assume the VDS is really small compared with the VGS minus VT, you can simplify this equation as the linear model within this region. And for this linear model, it can be replaced as the equivalent resistance. And this resistance equals to what we get ID over VDS. And this one can be 1 over mu n CR sine W over L over VGS minus VT. Okay, so actually the output voltage can be also simplified since we get this equivalent circuit as RDS. Here is the VDD, here is the output V out, here's the ground. So it's just like a voltage divider. We separate the voltage along this part. And since the RDS is typically small, so we can consider most of the voltage drop is along RD. Okay, so typically it will be 7 kilo ohm, and this one determined by this value. And we previously assumed the current should be high, so that we prefer to have a large term in the denominator. So the RDS is small in comparison with RD. So you can draw the scheme in which we get the input and output relationship as an inverter. So here is the output voltage, here is the input voltage. So what we get here is that if you draw the input and the output relationship again, before we get the input above VT, the output voltage will be still VDD or the total supply voltage here. So here's the VDD. But at times when we have the current flowing through the RD, it will continuously providing the ID and drop the voltage at the output. Okay, so you can see the current start to go up, and then we get the output keep on going down. Okay, so what happened here is in the saturation region. Again, remind you, BJT is active region. So here we have the saturation region. And then it will going down till what position? Till the lower position, which we get this going to the current. The current is too high, so the voltage drop along RD is large. And this one is large, that means your VDS no longer stronger than VGS minus VT, depending on how much you buy for VGS. The higher VGS you buy, the higher VDS is allowed, right? Because you can see the trial region relationship. The higher region you buy, you get a higher voltage along VDS allowed. And for this one, later it will go back the VD. And here is the part we call the high and low voltage. And the low voltage here. So you can think that by balancing at the different input and output, once your input voltage is really low, that doesn't turn on the circuit, you get the output as 1, which is VDD. But at the times when you have the input voltage as 0, that means as 1, you get a high voltage as the input voltage. That means you drive your circuit into trial region as the most base. And this trial region gives you current flow and go down the VDS. This VDS represents what is the output voltage. And for this output, its voltage is typically low. And for this one, it's typically 0.2 or 0.3 volt. Right? So that is the regular operations for all of these devices. Okay. We find some more interesting data. So maybe we go to the question first. We go to the slide first. Okay. So as we mentioned, here is the common source connection in which we connect the source to the ground. And then the input is from the gate, output is from the drain. And then currently we only consider the logic signal operation, which means that we have the DC biasing. And it is from like a DC biasing, like a logic signal operation. So we just have a DC signal. Once we fix the signal, we measure the output and what is the current and output. So if you connect the thing here, so you can see that we have the thermal state. So here's what we mentioned. There's the body. So for thermal state, they grounded it and then linked it as an arrow to the body. And then here's we get a 1 volt. And for 1 volt, it should get a conducting current. So if you compare the difference between 0.7 and 1 volt, you get a sweeping of the out input voltage of V2. So also by having the 0 volt, but in the PSpice you can sweep it. So we can draw the curve as the V2. Here's the voltage versus what is the current. Okay, so we try to increase the voltage along this power supply and see how much current we can measure at the drain side. Okay, so if you compare these two cases, the top ones we get the voltage at the gate side is 0.7, and the bottom one we get the gate voltage is 1 volt. You can see the drain current is 4 microamp, and then here is 10 microamp. We can increase the voltage, increase the current, which is proportional to VGS minus VT. So remember that in comparing with the saturation current, in most cases the current is not as strong as VJ. Because in VJ, what is the relationship? We typically say the IC proportional to IS multiplied with exponential VE over VT. So it is in its pleasure part. But here is we typically related to VGS minus VT squared. So you can see it's like a square term. So it doesn't strongly increase the current that much. Okay. But as I mentioned, there will be a really good benefit. There's no leaking current from the gate side. But you can also play with PSpice, place the current monitor at the gate side and see what is the corresponding current. Okay. Then you can see that after the trial region, the VG, the input volt, the V out, V2 or the VDS is high. So once the VDS is high, more than VGS minus VT, it is saturated. So that's why we call it the saturated region because the channel picture. Okay, you no longer provide more current going through because you get a limited capacity of your channel. Okay, even the driving voltage is high before you run your circuit again. Okay. So you can think that the saturation current will be just proportional to what we get from VDS squared. Okay, and here is the input of the relationship as we brought here. So you can think that here's we sweep the input from 0 to 10 volt, and here's the output measured here. So from the drain side. And then first, we still need to consider what is the full biasing, reverse biasing. And we get the input first sweep from 0 to 10 volt. We can clearly identify if your input voltage is smaller than 1 volt, the voltage is high. That means you get a high voltage at the maximum. But the layout will drop back immediately. But once you can identify in comparing with 3GT, which one gives you better interpretation? What does this mean? That means you get a steep slope. Which one gives a steep slope? This one gives a really smooth curve, right? As I mentioned, it doesn't increase the current significantly. It will follow like the VGS minus VT squared. So even you can play though, you get a small slope. That means if you work in it as an amplifier, the amplification is not strong. Okay, so that's also the reason why we typically use the MOSFET in digital circuit instead of in analog circuit. Okay, because the amplification is not really significant. But you can also see inside that if you work with the trial region, the voltage is down like less than 1 volt, depending on what is the resistance you apply there. Okay, so you can also replace with different resistance, like you get a higher resistance, you get a higher overloading along here and here. Okay, so when you are working with the trial region, it's just like a voltage divider. So if you can increase the RD, that means most of the power drop will be in RD instead of in RDS. So you can minimize your output. And also in digital circuit design, you need to know what is the minimum error you are allowed. For instance, you still have certain low level voltage, like 0.3, 0.1, even 1 more bit. So if you consider circuit like the VDD is 10 volt, that's definitely fine because typically is divided into 5 volts. If the voltage is higher than 5, we call it 1. If the voltage is less than 5, call it 0. So if your output voltage is 1 volt, it will be pretty safe to say it's low voltage. But unfortunately, sometimes we cannot use that high voltage because for your cell phone or digital circuit, typically the voltage should be lower than 5 volts. So divided by half, that means your voltage is less than 2.5 will be considered as the low voltage. But sometimes you want to use the even lower digital circuit stop line because we want to save battery. We want to get just 2 battery work with your device. Okay, so that will be a challenging thing. And here so we try to look at the model, especially we focus most in the model data. This one we will spend some time to discuss it, but I want to just say if you want to work in as the application amplifier, we want to get the input signal, the VGX as DC and AC current. And then for DC and AC current, you can separate the current and try to look at what is the corresponding slope. And similar to the BJT, we will try to again introduce you what is the corresponding small signal model. So that's what happens for the next class. Okay. So before I end the class today, any questions from the audience? Okay, so if there's no questions, thank you very much for joining the class today. Thank you.